Hi everybody, I am Shriya Talwar and I'll be taking your session today. So a little about me, I work with VMware as a member of technical staff. I have about 2.5 years of experience. I graduated in 2018 from MNNIT Allahabad, and then I joined Citicorp. After working there for a while, I switched to VMware and have been working here since then. So let's get started. I'll just share my screen. Yeah, I hope you all are able to see my screen. All right, I think it's a yes.
Yes,
So,
Shreya, we can, yeah.
all right. So before we get started, here's a little joke for all of you. I hope some of you will get this joke, and if some are not able to get it, I'll make sure that you get it by the end of this session. So let's go through the agenda of our session. First, we'll introduce ourselves to what is bit manipulation. Then we'll learn about some of the applications of bit manipulation. Then we'll learn about the common bitwise operators that are available. Then we learn about the common bitwise algorithms that we can perform. And then we'll be solving some of the interview questions with bit manipulation. And then there's going to be a small knowledge check to test your knowledge. So what is bit manipulation? Whenever we say bit or a binary digit, what do we actually mean by it? We know that all the information in the machines or the computers is stored in form of binary numbers, that is 0 or 1. So bit is essentially the smallest unit of data representation which our computers can understand. And what is bit manipulation? So if you transform the bits by any particular method to achieve some kind of output, that is what bit manipulation is. Now, there are some basic things that we need to know before diving into this session. So how is a binary number represented? So we know that binary number consists of 0 and 1. So let's say this is an 8-digit binary number. So each position of this binary number is, each position of this binary number is essentially the power of 2 increasing as we move from right to left. So you can see the rightmost number here is 1 and it is 2 to the power 0, and as we proceed towards left, the powers of 2 have been increasing. All right, and then we have the concept of LSB and MSB. That is, LSB is the least significant bit, that is the bit which is at the rightmost end since it is contributing to the least value, and most significant bit is the one at the leftmost end. All right, now why do we need to learn about these bitwise operators? So as programmers, the basic things we expect from our piece of code is that it should run as fast as possible. It should take the as least amount of storage as possible, and it should be compact and clean. Then we classify it as a good program, right? So bit manipulation can help us achieve all of it. It will cause an overhead, right? So the operations will take less time. Are you all able to hear me? I see a message saying that.
Yeah, you are audible.
Hello? Are you all able to hear me now? All right. Yes. So as I was saying, that bit manipulation can help us achieve fast operations. So for example, you want to multiply a number by 2. So one thing you can use is using the multiplication operator, but you can do it in a much faster way when we use the left shift operators. We'll know about them in the later sections of the session. And as far as storage is concerned, we can save that as well using the bitwise operators. So suppose you have to write a piece of code that allots permission to any file like read, write, execute, etc. So instead of storing each of these permissions, because these permissions will store the read permission is allowed or not, write permission is allowed or not, right? So instead of storing this in separate variables, you can simply use one byte and store all of these in the same byte. So this way, the number of data structures that you're going to use will be reduced, and the amount of memory will also be reduced comparatively. Now, other than that, whenever we try to communicate over any ports or sockets, we need to know about this concept, because the medium of transfer is generally in the form of bits. So whenever you want to perform some algorithms on the packets to check error detection, like the checksum or parity checks, etc., so these are performed directly at the bit levels. And then there comes data encryption and decryption and compression and all these things. So for doing all these operations, the data has to be extracted at the bit level, and that's why we need to learn about these operators. Now let's learn about some of the common bitwise operators that we have. The first one is the not operator. So not operator is basically the negation operator. It will invert any operation that any bit. Basically, if you try to apply not on 1, it will result in 0. And if you apply not on 0, it will result in 1. It's that simple. Okay. Now we learn about the AND operator. So a bitwise AND operator works on two binary numbers which are of the same length and compares each of the bits at the same position, right? So if we perform AND of any number, so if we try to perform AND of two numbers, the result will be 1 if both the bits are 1. Otherwise, in all the cases, it will be 0. So 0 and 0 will give us 0. 1 and 0 will give us 0. 0 and 1 will give us 0, and 1 and 1 will give us 1, because in this case both the bits are set. All right. So these are some of the common properties of AND operator. If we try to perform AND of any number with 0, it will always result in 0, because because one bit in that case will always be 0. And you can see from the first three rows in the truth table that this should lead to 0. The second one is if we try to apply AND of any number with its complement. Okay, so that will result in 0. Let me explain you how. So suppose we have a number like 1010. So if we take the complement of this number, it will become like 0101. And if we perform AND with the original number, we can see that each of the bit has been inverted. So there will be no instance when both the bits are 1. So we will get the number 0 as the answer. I hope that makes sense. All right. So the next is the bitwise OR operator. It works similar to the AND operator, that is working on two binary numbers with the same number of bits and comparing the corresponding bits, except in this case, the output of OR operation between two bits will be 1 if either of the bit is set to 1. If both the bits are 0, the answer will be 0. So if we fill out this truth table, 0 or 0 will give us 0, 0 or 1 will give us 1, 1 or 0 will give us 1, and 1 or 1 will give us 1. Okay. Now, some properties of this operator. So whenever we perform AND of any number, OR of any number with 0, it will result in the same number. Because, okay, let me explain you how. So if we have a number like this and we perform its OR operation with 0, simply, since either of the bit is set, this will return 1. None of the bit is set, it will return 0, and one bit is set, so it will return 1. So we are going to get the same number. And if we try to do the complement the OR of a number with its complement, it will return in a number with all the bits set, because either of the bit is going to be 1. Now we have this XOR, or the exclusive OR operator. So this operator works in a little bit different way. It will return the value 1 only when both the bits are different. Otherwise, if the bits are same, it will return 0. So filling out this truth table, zeros or 0 will give us 0 because both the bits are same. Zeros or 1 will give us 1 because both the bits are different. Ones or 0 will give us 1, and ones or 1 will give us 0. And some common properties about this operator is, if we try to XOR of any number with itself, it will give us 0 because all the corresponding bits are going to be same. Now, and if we try to do XOR of any number with 0, it will return us the same number, because what XORing with 0, what it does is, if you see the first entry and the second entry, you will see that the number remains the same, because when we are trying to do XOR of 0 with 0, it is giving us 0, and we are trying to do XOR of 1 with 0, it is giving us 1. So the number will remain as is. And if we try to do XOR of any number with a number of equal length having all the ones, it will return in the complement of that number. So for this, let us take this example again. We have this number 1010, and we have a number with all ones. So we know that if we try to do OR of XOR of different numbers, it will give us 1. In this case, it will give us 0. In this case, it will give us 1, and ones or 1 will give us 0. So clearly you can see that this number and this number are complement of each other. Any doubts so far? Moving on, we have two more operators. The first one of which is the left shift operator. So whenever we perform an operation like n left shift m, what it will do is shift the number n by m positions towards the left because it's the left shift operator. You can see this number on the right hand side. So in this case, the number on the number above is being shifted towards the left by one position, and as you can see, a number 0 is being appended towards the end of this number because we need to maintain the length, and the numbers which were at the front will be truncated. And if you try to understand what this operator is trying to do, it is essentially multiplying the original number by 2 to the power m. So we can see this. The left shift operator. Hello.
Hi, Yash.
Hey, hi. So actually,
Yeah,
I wanted to know the all operators real life application, because we are learning this since our college, but no one taught this where to be used in the real life application. So I was just curious about this thing.
okay. Yeah, so we will like learn about it in the consequence section. So I'll tell you how do we apply these.
Yeah, okay.
Actually, one application I would like to mention about is that we will use this in routing context. So where you need to match for the uh, prefixes and everything, right? So in that case, these bitwise operators would be useful. So yeah, we can give you some pointers. Let Shreya continue with all the concepts.
Yeah, okay. Yeah, no problem.
Hmm. All right. Yeah. So as I was saying, so this will essentially do a multiplication of that number by 2 to the power n. Okay. So now if we want to left shift a number 4 by 2 positions towards the left, so we know that 4 is represented as 100, and when we try to do a left shift by 2 positions, what it will do is add 2 zeros towards the end of this number. And if you know the binary conversions, so you'll understand that this is essentially the representation of the number 16, because this is 2 to the power 0, this is 1, this is 2, this is 3, and 2 to the power 4. Okay, so what is 16 actually? It is 4 into 2 to the power 2, and where 2 was the number of bits we were trying to shift. All right. Now, the next one is the bitwise right shift operator. So the right shift operator does the same work as the left shift operator, except that it moves the bits towards the right hand side. So in this, on the right hand side, you can see that this number is being shifted towards the right by 1 bit. And in this case, the number 0 is being prepended at the end of this, at the beginning of this number. And what this number is trying to do is simply dividing it by 2 to the power m. All right. So if we try to perform a left shift operation on 4 by right shift operator on 4 by 2 bits, so this will shift the number by 2 bits. So the number will become something like this, that is 1, and which is essentially 4 divided by 2 to the power 2. Yes, Akshay, for sure. So in this, what I mentioned was the left shift operator, what it tries to do is multiply that number by the number n is being multiplied by 2 to the power m whenever we apply this left shift operator. So I can give you one more example of this. So if you have a number 8 and we are trying to do a left shift operation on this by, suppose you say 2 bits again, okay? So this number 8 is represented in binary like this. And when we want to shift 2 bits, what we will do is we will add 2 bits towards the end and this number will be moved towards the left. So this was the original number. We added 2 bits, that is zeros, at the end of this number. And this number is, so if we go by the power of 2, so this is the 2 to the power 5, which is nothing but 32. Okay. And this number 32 is nothing but 8 into 2 to the power 2, and where 2 is the number of bits that we are trying to shift. I hope that makes it clear, Akshay.
Yes, thanks.
All right. Yeah. So then this was the right shift operator. I hope this was clear. Now that we know about the common bitwise operators, let's have a small knowledge check. Okay. So you can use the chat to answer these questions. What should be the output of this operation? Yeah, so most of you are giving the correct answer. So what is doing is basically 1 and 0 will give us 0. And then when we try to do XOR of 0 with 1, since the bits are different, the output will be 1. Okay, so let's try the next one. What should be the output of this? In this binary number is being shifted towards the left by 2 bits. Okay, so let me just solve this for you. So yeah, one thing that I wanted to mention here was that whenever we work with binary numbers, generally we know that the length of the binary number that we should have. In this case, the binary number is of length 8, right? Because there are 8 bits present. So now, assuming that we are working with the binary numbers of length 8 only, whenever we try to do a left shift on this, what it will do is these 2 bits, the first 2 bits will be removed and the number will become something like 0, 1, 0, 0, 0, 1 and 0, 0. All right. So, and if we go by this, so what this is 2 to the power 0, 2 to the power 1, 2 to the power 2, 3, 4, 5, 6, 7, right? This was 64 and this was 4. So the answer in this case is going to be 68. And yeah, some of you were right. And for others, I hope it cleared. All right. Now, what should be the answer of this? In this case, we are right shifting the number by 3 bits. Sorry. All right, Shilpa says 24. Let's just wait for other folks. Okay, so most of you are saying 24. Let's try it out. Okay, so whenever we try to do a left shift or right shift, in that case, the numbers will be moved towards the right, and since we are moving by 3 bits, so 3 zeros will be added towards the front of this number. So what will happen is these 3 bits will get removed from the original number. We can have 3 zeros here, then 1 1, and then 3 zeros here, and then this is 0 1 2 3 4. So this is 2 to the power 3, that is 8, and it is 2 to the power 4, that is 16, and 16 plus 8 is 24, as most of you said. All right, shall we move on to the next question? Okay, so you know how to perform a left shift and a right shift. What if you are asked to perform a circular shift or rotation of bits of a number? So what do I mean when I say that? So suppose we have this number 10001110, and we want to rotate it anti-clockwise, in the anti-clockwise direction, that is towards the from left to right. So if you want to rotate it anti-clockwise by 2 bits, so what we are trying to do is we will move this number towards the left by 2 bits. And now in case of normal left shift operator, what we would have done is after shifting it by 2 bits towards the left, we would have added zeros. But we are not performing a left shift. We are performing a rotation here. So instead of adding zeros, what we'll do is we'll move the numbers from the front of this number towards the back. So this number will become like this. Okay, I hope all of you got what the question is. Can you guys try how to compute the formula for this?
Please repeat, please, sorry, please.
Yeah, it's all right, all right. So what this question asks is that we need to rotate a number by a certain number of bits, and while rotating, we'll always be knowing what is the direction that we want to rotate. In this case, we want to rotate it anti-clockwise. So as we know, the anti-clockwise direction goes like this. So what will happen is 2 bits of this number will move to the back of this number. So if we want to rotate it by 2 bits, the number will become 0 0 1 1 1 0 1 1. All right. So we need to find out how can we achieve that using our bitwise operators. I hope the question was clear now. I'll give you guys one more minute to try. All right. So let's walk through the solution for this. Okay. So how to approach these kind of problems? So we know that the number is 11000, sorry, 110 and 1 just a second. Yeah, 110. All right, and we want to perform the rotation. So for the expected answer is this. Instead of getting them, okay, we have one solution. Okay, we'll just try that also. Okay, so in this case, what we'll do is, we know that we want to achieve something like this, that the 2 bits or the k bits should come behind and the rest of the number should be shifted. Okay, so what if we try to divide this in 2 parts and try to achieve each of the part individually from the original number? Suppose we divide it like this: 00111 and followed by 2 zeros, and for this part we can have 00000 and 11. All right, so and if we are able to achieve these two parts and we try to perform a union of those or perform OR, so we know that whenever we try to perform OR of any number with 0, it will return in the number itself. Okay, so what will happen is, these zeros when ORed with this part will give us this number itself in the last 2 bits, and the rest of the number will be copied from this part of the number. All right, and the number will be rotated. So I hope till here it was clear. Okay, now how are we going to achieve this part and this part individually? So this part, to achieve this number from our original number, what can we do is simply apply a left shift here. Okay, because we know that if you want to append 2 zeros to any number, we can simply left shift by 2 positions. So if we try to apply left shift on this number by 2 positions, the answer will be 001110000. All right, and if we want to achieve this second number from our original number, so whenever we want to move a number towards the right hand side, so we try to perform a right shift. And by how many positions we are going to perform a right shift? The n minus 2 positions, because we want only these 2 bits to remain at the end and the rest of the number should be 0. So if we perform a right shift by what, n minus 2, that is 8, that is the length of the number, by 2 positions, so this number will be shifted by 6 position towards the right. So in this case, 6 zeros will be appended or will be prepended, and the 2 bits will remain as that. And now we'll perform the final OR operation: 001110000. So this is the first thing which we achieved. This is the second number that we achieved. Now we are performing OR of 1 and 2. And this will simply give us 1 1 0 1 1 1 0 0. I hope the explanation was clear. Okay, and if we try to derive the formula for this, is what we did here was, what we shifted the number n by k bits. In this case, k was 2, and we performed OR with the number which we got when we shifted the number by towards the right by n minus k bits.
I would like to clarify that this n in the second formula is the number of bits, not actually the number, right?
Yeah.
So this n, maybe you can put capital N, right, to represent that
Yes.
how many bits are going to be there in the number.
Yeah.
Yeah. Correct. Yeah. So Vivek, your answer on the left side is correct, but the right side you have to right shift by 8 minus k
bits.
number of bits.
Yes.
Yeah.
Yeah. Thanks.
Yeah. Yeah, Shreya, continue.
Yeah. So shall I move on to the next part? Okay. So now we know about the basic operators. Let's see where are we going to apply these operators? Like where can we use these operators? So the first one is basically finding the 2's complement. Okay, whenever we store information, we know it is stored as binaries numbers. Okay, and so we needed a way to represent the negative numbers, and 2's complement is nothing but that. So how is 2's complement calculated? It is simply the 1's complement of the original number with 1 added to it. Okay. So suppose we want to calculate, we have a number 4 and we want to calculate the value of minus 4. So what is the binary representation of the number 4? So here we are going to assume that the length of the binary number is 4 only. Okay, we are working with binary numbers of 4 length. So the number 4 in binary notation will be 0, 1, 0, 0. And now we'll do the first step, that is finding the complement of this number 4, which will be 1, 0, 1, 1. And then we will add 1 to it. So let's add 1 to it. So this is how binary addition works. 1 plus 1 will be 2, but 2 is represented as 0, 1 in this case. So 0 comes here and 1 will be carried over. Then 1 plus 1 will give us 0 and 1 will be carried over here and it will come here and 1 will be copied here as like this. So the representation of minus 4 is 1, 1, 0, 0. And in case of 2's complement, we can always, in case of negative numbers, we should always note that the most significant bit of that number will always be 1. It will never be 0 in case of negative numbers. Okay. And this actually helps in simplification a lot. So suppose we want to calculate a minus b. So instead of doing the binary subtraction, what we can do is a plus minus b, and where b minus b is essentially the 2's complement of b. I hope it makes sense. Yeah. So just move on to the next one. So next one is identifying the kth bit. So we have been given a binary number n and we want to know if the kth bit of that number is set or not. When we say a bit is set, it means it is 1, and when we say it's not set, it is 0. So here also we are assuming that the length of the binary numbers is 4. So suppose n is 1010, okay, and the value of k is given as 1. So whenever we count the binary numbers, we start from count the position of binary numbers. We start from the right end, and the first position is the 0th position. So the k is equal to 1 refers to this position. Okay. So we want to know that this bit is set or not. In this case, it should return true, or it should return as 1, that the bit is set. Else, had the value of k been 2, so we would want to identify this bit, and in this case the output would have been 0 or false, that this bit is not set. Okay, So we want to achieve this. Now, so we know the number is 1010 and k is equal to 1. Okay. So we want to perform some operation with this number such that when that operation is performed, the output should give us something which will help us identify. Okay. So let us think of some common operators. So we know that if we want to do AND of any number with 1, okay, so it will give us that number itself. AND of 1 with 0 will give us 0, and if we try to do AND of 1 with 1, it will give us 1. Okay, so if we try to have a mask or a number such that the kth bit is set to 1 in that case, and we try to perform AND of this number with the second number, we should get some kind of information. All right. So what should be, so we need to think that what should be the other bits in this case. One more thing that we know about the AND operator, that if we perform AND of any number with 0, then it will return in 0 always, because none of the bits is going to be set. So this is 0 and this will also return 0. So if we have something like this, what will happen is, in this case, if we perform AND of these two numbers, it will give us 0, 0, 1, because these two corresponding bits are set, and this will return as 0. So this is some non-zero number. All right. Now, if the value of k had been 2, okay, so in this case, we would have wanted our second bit to be set and rest of the bits to be not set. And the output which would have been obtained in such a case would have been 0. Okay, so what we can conclude from here is, if the kth bit is set, the output of this and this number will always be non-zero. And if the kth bit is not set, the output is going to be 0. Okay, and how do you achieve this kind of number? Any guesses, like how can we achieve this number given we have k and we have n? Yes, most of you are right. So we are going to left shift the number 1 by k positions. So in this case, the value of k was 1. So 1 shifted by 1 position will give us 1 0, and in this case it will be 0 0 1 0, and in this case 1 shifted by 2 positions would have given us 0 1 0 0. All right. So what do we get from here is n and 1 left shift by k. If the answer achieved from this operation is not 0, then kth bit is going to be set, and otherwise if it is 0, then the kth bit was not set. Any doubts with this? Okay, so let us know where we can use this kind of operation. So we can use it whenever you want to check whether a number is odd or even. So let us see how are basically numbers represented in binary forms. We'll check just a couple of these. So 1 is represented as 1, 2 is represented as 1 0, this is represented as 1 1, 4 is represented as 1 0 0, 5 is represented as 1 0 1, and 6 is represented as 1 1 0. Okay, so one thing which we can note here is 1, 3, 5, that is all the odd numbers, will always have their last bit or the least significant bit as set. You can see from here. And in case of even numbers, the least significant bit will never be set. Okay, so we can simply derive this from this, because we want to identify the kth bit, and in this case the value of k should be 0. And whenever we try to perform AND of any number with 1, this k is 0 here. So, and essentially this is n and 1, because 1 shifted by 0 positions is 1 only. And the output, if the output of this is 0, then the number is going to be even. And if the output is not 0, then the number is going to be odd. So instead of using the modulus operator, you can just get it in one line. All right, so I hope it was clear. Okay. So now we are going to check whether the kth bit is set or not set. So what do we mean by this is, suppose let's take the same number again. Suppose we have this number and we want to check if kth bit, that is the first bit, is set or not. So sorry, we need to set the kth bit. All right. So the value of k is 2 in this case, and the output of this setting the kth bit should return us 1 1 1 0, because we had to set this bit, and after performing some kind of operations we are going to achieve this answer. Okay, now to do this, let's think what operations we can perform. Okay, we know that we want to set this bit. Now we need to think of some operator that will help us set a bit irrespective what its value is. So we can think of an OR operator in this case. If we try to do OR of any number with 1, it will always give us 1, because either of the bit is going to be set in that case. And so we want to have a mask or a different number here such that this value is going to be 1, the kth bit is going to be 1, and we are going to perform OR operation. And what about the rest of the bits in this number? We know one more property of the OR operator, that if we try to perform OR of any number with 0, it will give us the same number itself. Okay, so here the OR was applied with 0, and here the OR was applied with 1, so the answer was 0 and 1. So if we have something like this and we perform OR of these two numbers, so the rest of the bits are retained as it is, and this bit, that is the kth bit, is going to be set. Okay, and how we achieve this, we know from the previous question that we can simply achieve this by shifting the number 1 by k positions, and where k is equal to 2 in this case. So when we shifted 1, so it resulted in this number. So what we did here was, we first formed a mask by getting the kth bit as set and rest of the bit as unset, and we performed OR of that number with the mask, with the original number with the mask. Okay, let's just see the formula for this. So this is what we have done actually. Okay, now the next one is unsetting the kth bit. So what do we do? When we want to unset the kth bit? So let's take the same number. Let's take a different number this time. All right, and we want to set the kth bit, that is k is equal to 1. So the output of this number should give us this, where the first bit is not set. Okay, so how are we going to achieve that? Now again, we'll think of some operator that will help us unset this bit irrespective what it is. Okay, so any of you can guess which operator or which operation can we use? Okay, Shilpa, so not operator will give us the complement, right? So NOR of 1 will give us 0, and NOR of 0 will give us 1. So this won't work. We want to get the answer 0 in all the cases. Okay, so Kiana, n and 0 shifted by k will basically give us Okay, ANDing any number with 0. This will always give us 0. Okay, we can think of it. Ashish, yes, you said AND, but with what? Okay, so yeah, so Kiana, your logic is right and we can use it. So we had a number like this and the value of k was 1 in this case. All right, so we want to have a number such that this position is 0 because we want to AND the number with 0. Okay. Now, what should be the value of rest of the positions? We know we are going to use the operator and we know that this bit is set to 0. But if we have a mask such that we have 0 0 0, we have a number which is all 0, then in that case the and if we try to AND it with the original number, in that case the answer will come out to be all zeros. And we don't want all zeros. We want something like 1100. Only this bit should be set to 0. Okay. So, Kiana, your answer was partially correct actually. Okay. So, one thing is that is clear that we want something like this here. Okay. But rest of the bits, if we are trying to use the AND operator, we need to have something by ANDing. If we try to AND one number by that number, it should always return in the original number. Okay. So if we try to perform AND of any number with 1, it will return in that number itself. All right. So 0 and 1 will be 0 and 1 and 1 will be 1 because the original numbers were these. So what we want to achieve is that a number which we are trying to AND with the original number should have kth bit as not set and rest of the bits as set. So let us think how we can achieve this. Okay, in XOR 00K. So essentially we are trying to do XOR of any number with 0 and it will give us the same number itself actually. Shilpa. Okay, so if we look closely at this number, what it is it's simply the complement of this number. And we know that how we can achieve this number. This is nothing but left shifting 1 by k positions or 1 position. And the second number is the complement of this number. All right. Okay, so yes, Kiana, you're right. So what we did here was we tried to compute one mask which we can use to perform AND operation, and that mask was achieved having not of 1 shifted by kth bit, and we tried to perform AND of number with mask. All right. So yes, this was the answer for this one. Now let's learn how to toggle a bit. So what do we mean when we say we want to toggle a bit? It is simply saying that if a bit is set to 1, set it to 0. Otherwise, if it is set to 0, set it to 1. So if in this number k is equal to 1, so this bit was set, the output of this should give us 100. And if the value of k was 2 for the original number, it should have toggled the second bit, that is, it should have set the second bit in this case. All right. So, okay, now we need to achieve this kind of operation. So, just like all the other cases, we need to, so in this case, we are working for k is equal to 1. We need to have some operator that if we apply at this, that is the kth position, it should invert it. Okay. And we learned about it when we were learning about the bitwise operators. Can any of you think about it? Yes, most of you are trying to get the entire formula correctly. That's great. Okay, so I'll just try to explain for the others. So we know the property of a XOR operator, that if we try to perform XOR of any number with 1, it will simply invert that number, because XOR of 0 with 1 will give us 1, and XOR of 1 and 1 will give us 0, because these two bits were same. Okay, so we know that we need to have a mask such that the kth bit is set to 1 in that case, and we know that the operation we are going to perform is the XOR operator. So what should be the value of other bits? We know that XORing any number with 0 will result in that number itself. Okay, so we can easily have these numbers because we don't want to disturb the rest of the numbers apart from the kth number. And when we try to achieve the XOR of these two numbers, so it will give us where kth bit is going to be toggled or not set. Okay, so this is NXOR 1 1 left shifted by k positions. Okay, now the next part is counting the set bits. So counting the set bits is basically we have a number n where we need to count how many of the bits are set. So in this case, we know that 2 bits are set, so the answer should be 2 in this case. Okay. So let us think how we can achieve this. Now, for a given number n, if we try to, let's learn about one more thing. What happens when we try to perform n minus 1? Whenever we try to subtract any number with, whenever we try to subtract 1 from any number, let's see what happens here. So this will give us 1 because this will borrow here and this will become 1 0, and then this will become 0, and these two numbers will remain just like this. And okay, and if we perform one more subtraction with 1, so this will give us 1, this will give us 1, this will be done, and this. Okay, so what happens if you observe is whenever we try to subtract minus 1 from any number, from any binary number, it will invert all the bits till the first set bit. So these bits were inverted, that is 1 became 0 and 0 became 1. And in this case also you can see the first set bit was here. So the numbers are going to be inverted like this. 0 became 1, 0 became 1, 0 became 1, and 1 became 0. Okay, and if we try to do something like n and n minus 1, okay, so in this case the original number was 1010 and n minus 1 is going to be 1001. So performing AND of this number will just unset the first set bit from the right hand side. So you can see the original number was this and first set bit was this. So this bit has been unset. Okay, so this is setting the first set bit from the right hand side. Okay, so we know what this operation does. So in the original number, now we have only one bit set. What if we perform this operation again on this number? Okay, let's try to do that. So we know 1000 minus 1 is going to give us 0, 1, 1, 1. And if we perform AND of 1000, 100 with 0, 1, 1, 1, and perform AND of these two numbers, so this will give us 0. All right. So in this, now the number which we have achieved has all the bits unset. All the set bits have been inverted and they have become unset. So from this we can understand one thing, that if we try to apply this operation multiple times till the original number becomes 0, then, and we keep on increasing the count, then we can get the number of number of set bits. So let's just explain it with this code snippet. So what we are trying to do here is we are checking till x is not 0, we need to keep performing the AND operation of x with its 1 less than x and keep increasing the count. Okay, any doubts in this?
So I wanted to take up the earlier question where someone asked how bitwise operations are applied in real world scenario and all, right? So let's say that you have represented like you want to post something and you want to post it to only your friends, not your work colleagues or something like that, right? Let's say that in that social platform, uh, the friends are listed as a bit mask kind of thing, right? How do you find out effectively that you need to post this to a certain person only and not the other persons, right? So you can think of applications of bitwise operations like that, right? So instead of so let's say that you have to post this update to a set of people out of all connections, right? So consider, I mean, this count set bits thing could be one of that scenario, right? How do you find out how many updates you have to post, or I mean from the backend, right? So and if you go by, see, there are other brute force methods to it, right? So Shreya has already talked about, if you want to find out from the left side whether this particular bit is set or not, you have to do n traversals in the bit mask. But this is one efficient way where you can just traverse the list only the number of times the bit is set. So that is the efficiency of doing the bitwise operators here. The x and x minus 1, right? Because of the way how the bits bit manipulations work, you could achieve this in smaller number of operations itself. So I hope that makes it clear.
Yes, thanks, Susanna. Okay. So, any doubts here? Okay. So, at one place where this bits, so there are places like Usaina mentioned that we can use this kind of algorithm to do. So, at one application of this is checking if a number is a power of 2 or not. Okay. So, let us see that how the powers of 2 are represented in binary notation. Okay. So, one thing we can observe about these power of 2 is that in all these cases, there is only one bit set. All right. So, using this, we can get if a number is a power of 2 or not, because what we'll try to do here is we'll try to perform the AND, we'll try to perform this algorithm and then simply compare if the value of count is equal to 1 or not. If the value of count is 1, then the number is going to be a power of 2, otherwise it's not. And we can further simplify this, because in this case, the loop, it will break out of the loop in the first time itself because the count is 1. So instead of having the loop, we can simply use this statement with x and x minus 1 to check. And if the value of this is going to be 0, then we can assume that this number is a power of 2. And if it is going to be non-zero, then it's not a power of 2. All right. So of course there are other methods to check if a number is a power of 2, like by dividing the number constantly by 2 and checking the remainder is 0 or 1 or not. But as Husaina mentioned, that this algorithm will result in less number of operations and make the code efficient. Okay. So let's move on. So now we know some of the basic algorithms also, and it's time that we we solve some of the interview questions now. Okay, so the first question here is, we have been given an array with n distinct numbers in the range 0 to n and we want to return the number that is missing from the array. So for example, we have been given a value n is equal to 3. Okay, so now we know that the array has size 3. So numbers from 0 to 3, both inclusive, can be present in that array. But so that makes it 4 numbers, but only 3 numbers are present. So 0, 1, 3. In this case, we know that the number 2 is missing, and we need to basically we need to find out that missing number. I hope the question was clear. Okay, so I guess it's clear to all. Now we need to solve this question. So the one way to solve this question is simply traversing through the array and maintaining the frequency of each element in a separate array. Suppose we want to traverse this array, we know that the frequency of this is 1, this is 1, and yes, max array length is n. And so we will know that the frequency array will contain the frequency of each element. So the frequency of all the numbers present in that array is going to be 1 except a number that is missing. And we can simply check that by checking at which index the frequency is going to be 0, then that is the missing number. All right. But this will cost us extra space of O of n, that is where n is the size of the array. What if we want to perform this operation in a constant space? Okay. So here we are going to use the bitwise operators. Let us see how we can use it. So we know some of the properties of a bitwise XOR operator. Basically, if we try to perform XOR of any number with 0, it will result in the same number. And if we try to perform a XOR of any number with itself, it will return in 0. All right, so maybe we can use this property of XOR operator to solve this question. Now we have two sets. Okay, the first set, we know that all the numbers should be in the range 0 to n. So where in this case n is equal to 3. So first set will have 0, 1, 2, 3. And the second one is the array itself, which we have been provided in the question. So this will have 1, 0, and 3. So you can see that the element which is missing is not present in the second set. Now, all we have to do is basically perform the XOR of all these numbers. So if we try to do that, so what we're going to do here is 0, XOR 1, XOR 2, XOR 3, XOR 0, XOR 1, XOR 3. You can see this is from the first set and this is from the second set. So 0, XOR 0, since these are the same numbers, will give us 0 because n is 0. Then 1 XOR 1 will also give us 0 because these are the same numbers. Then 3 XOR 3 will give us 0 again, and one number that is left is going to be 2. Okay, and XOR of any number with 0 will give us the same number, so we can find out the missing number in this case. Okay, so let's just walk through the algorithm for this one. So what we did here, we computed the size of the array and we allotted a result, initialized the result with 0. Then as we move from 0 to length, so basically here we are performing XOR of all the numbers from the range 0 to n and storing them in the result. Okay, so this operation is basically doing 0s or 1s or 2s or 3. And then we are traversing the array and XORing them with the value which is stored in the result. Okay, and here basically this is suppose R1. So this R1 is being XORed with all the elements of the array, that is 0, XOR 1 and XOR 3. And then the effective answer, that is the value which will be stored in the final result, will give us the answer, that is the missing number. And in this case, it's going to be 2. I hope this was clear. All right.
One real life
Yes.
example, what we can think of is like, let's say that you have sent out n packages and you have to figure out which package was missing, right? So there are scenarios like that in which you can find out that which particular package went missing, right? So if you have acknowledgement for the rest of the packages and not for one, right, and you have to find out which package went missing, right, then you could do this, right?
Yes.
Like real world example. Yeah.
Okay. All right. So this is one more on the right hand side. We can see one more way to approach this problem. Essentially, instead of doing it in two separate loops, we can combine this in a single loop itself. By what we are doing here is basically we know that the indices will also be storing values from 0 to n minus 1. Okay. So what we'll do is we'll simply perform the XOR of the result with I, that is the index, and the element at that index. And since in this 0 to n minus 1, we have the original length missing, so we'll just store it in the result at the first place itself, so that we can achieve the similar kind of operations and the similar result in this case. Okay, if there are no doubts, I can move to the next question. No, Ruturaj, this is not valid for a sorted array because basically we are performing a XOR operation and it doesn't depend on the ordering of the array. Because had it been something like fives or twos or ones or three, so in any case, essentially, and okay, threes or one, so the similar numbers would have cancelled out in any order because they are also being XORed together, right? So this would have given us 0 and this would have also given us 0. So essentially the output of this would have been 5s or 2. So this
Okay,
can
I think we should say that the constraint here is that it has to be all natural sequence numbers, right? So
yes.
basically it's everything is included and one is missing. So yeah, there is a sequence. The number should be a natural sequence. Yeah.
Yes, Vivek is right. Okay. So now let's move on to the second question. So now in this case, we have an array which has all the elements which are appearing twice, and there are two elements present in that array which occur only once. So for example, we have this array like 4, 2, 1, 3, 5, 2, and 4. So in this case, you can see the number 1 is appearing twice, number 4 is appearing twice, number 2 is appearing twice, and these are two elements, that is 3 and 5, which are appearing only once. So we need to find out these two numbers. That is, the answer should return us these two numbers which are appearing once. All right. So following from the previous question, we know one property of XOR, right? That if we try to do XOR of the same numbers, it will return in 0. Okay. So let's try to do the same thing here and let's see what can we achieve. So if we are going to do XOR of all the elements in this array, so let's do that. Okay. So 1 XOR 1 will give us 0. Then 4 XOR 4 will give us 0. 2 XOR 2 will also give us 0. And since there is no number similar to 3, so it will come as is, and this will give us 5 because we don't have a duplicate of 5 also. Okay, and this will essentially give us 3 XOR 5. And if we try to represent them in the binary form, So 3 is represented as 0, 1, 1 and 5 is represented as this. And if we perform XOR operation between these two numbers, so 1 XOR 1 is going to be 0, 1 XOR 0 is going to be 1 and 0 XOR 1 is going to be 1. So we will get a number something like this when we're trying to perform the XOR. So now we don't have our expected answer, right? But we know that it is hidden somewhere in this number because we know that this is a XOR of two numbers which are appearing once. So we need some way to extract out these two numbers. So what we are going to do here is, let's just try to observe this number here. Okay. So one thing that can be a differentiating factor is between the two numbers is if we look at the set bits in the XOR of this number, then what will happen is we can see that the bits which positions which are set, these numbers would have had the corresponding different bits. So if you see this first position, that k is equal to 1, at this position the number 5, the bit was unset, and in number 3 the bit was set. And same goes for the k is equal to 2 position, that one of the bit was set and the other bit was not set. Okay, so if we try to find some way to segregate these into two groups where we take one position, suppose we are taking the the bit, the first set bit basically. So in this case, we are considering only this position. Okay, so if we try to divide the numbers of the numbers in the array in two groups such that in one group the bit is not set and in the other group this bit is set. Okay, so let's see if we can do that. So we have our numbers like 1, a binary representation of 1 is 1, then binary representation of 4 is 100. Okay, so let's represent it in sorry, so let's just represent it in length of 3. Then we have the number 2, which is represented as 010. Then we have the number 3, which is 011. We have the number 5, which is 101, and then rest of the bits are same only. Rest of the numbers are same. So we know if we take this number 1, we know that this bit is not set, so it will come in this set. We have the number 4. In this case also the bit is not set, so it will come again in this set. Then we have the number 2. In this case, this bit is set. Okay, we are looking at the first bit. So this will come in this set. Then 1 again will come in this set. Then 3, we know that this kth bit is set in this case, so it will come here. Then 5, we know that it wasn't set, so this is going to come here. And then we have the number 2, which will come here, and we have the number 4 that will come here. So now we have two sets, the first set where the kth bit is 0 and the second set where the kth bit is 1. Okay, so okay, so can we try to extract the numbers from this now? Okay, so yes, we can actually. So if we try to perform XOR within this group only, so what will happen is 1 and 1 will cancel out, 4 and 4 will cancel out, and the remaining number is going to be 5. And if in this set we try to perform XOR of all elements, 2 and 2 will cancel out and the number effectively will be 3. So we have now tried to, we have not now successfully separated these two numbers, that is 5 and 3. Okay. So I hope this explanation was clear. All right. So
Shriya,
yes.
to reiterate, right? So we first did XOR of all the numbers, and then we went to the first set bit, right?
Yes, yes.
And then we did the left shift by that position, right? And then we did and with all the numbers, and then based on whether it is 0 or whether it is 1, we have divided the numbers and placed them in two different categories, and then did XOR of all that, right? I think instead of placing them in a different memory, we could just keep on XORing them as well, right?
Yes, yes, yes.
Yeah.
That's
So
just
then the final, yeah.
Hmm.
So if it is 0, you keep on XORing result 1. If it is 1, you keep on XORing result 2. And basically result 1 and result 2 would contain those two numbers.
Yes, absolutely. So, okay. So one thing that I didn't explain here actually was that how are we going to identify that which bit we are checking for whether it is set or not in all these numbers. Okay. So we know that we are checking the most significant bit, but how are we going to identify in the code? Okay. So let's just walk through the pseudocode and I'll explain you. So, okay. So the first part of this, you can see that we are trying to XOR all the elements in that array. So that was the first step where the output we achieved was 3 XOR 5 and rest of the elements were cancelled out. Then we need to have a mask such that we can just, so in this, we need to have mask where only the first set bit was present and rest of the bits were 0, because then we can perform our algorithm to identify the set bit, identify a particular bit. Okay. So let's see how does this mask work. So we have a number x. So in this case, our number x was basically XOR of these two numbers. So this was this, x was 110, and now we are going to perform a minus x operation on this. So minus x is nothing but the 2's complement of x. So this will be 001 plus 1. So, okay, so I guess, wait a second. I guess I messed something out. Yeah, all right, okay. Yeah, that was correct actually, sorry. So we tried to perform the complement of x and that was 001, and then we want to add 1 to it. So this will be 0. So in this case, actually the 2's complement, the most significant bit is not set because the original number was itself a negative number, because this most significant bit you can see is set here. All right. So, and if we perform the AND of the original number with its negative number, what you can see here is, sorry, yeah, so we can achieve a number such that only the kth bit, that is the first significant bit of that, the first set bit of that number is going to be set, and the rest of the bits are not going to be set. So this is how we achieved our mask. And then what we simply did was iterated through the array again and performed the algorithm for identifying if a particular bit is present or not. In this case, this was the first bit, and if it was not present, that is the result was 0, then we set it into the this result, that is num1 is storing the result of the set which had the kth bit as 0, and num2 is storing the result of the set which has the kth bit as 1. All right, so this way num1 and num2 will give us the numbers that are appearing twice, that are appearing once. Again, this will take a constant space and it will work in linear time. Any doubts here? Okay. So now let's move on to the next question. So this question is basically finding out the power set of a set. Power set is nothing but a set of all subsets of a particular set. So suppose we have been given a set like 1, 2, and 3. The power set of PS will be comprising all the subsets that are possible out of this. So one of the subsets is going to be an empty set where none of the elements are going to be present. Then there's going to be 1 where each element is present once. Then we are going to have a set of each of the pairs, just 2, 3 and 3, 1. And then we are going to have a set where all the elements are going to be present. Okay, so this is how we are going to achieve. So this is what a power set is. Now, how can we achieve this? So there is one way by using the backtracking method, but what we are going to, so since this is session on a bitwise manipulation, we need to think of it in the bit way. Okay, so how can we achieve this using the bits? So one thing we need to note about the power set is that the number of elements in the power set will always be in the form of 2 to the power number of elements in the original array. That is this. So in this case, n was 3 because there were 3 elements in the array. So the number of elements in the power set are going to be 2 to the power 3. And you can see for yourself 1, 2, 3, 4, 5, 6, 7, 8. There are 8 elements present in this. All right. And one more thing which we can do is, so we can make an analogy. So for solving this, we can have something like, we can have binary numbers of length 3, where each position of that number will represent 0 or 1, since it's a binary number. And if we compare that to the power set, we can have, if the particular bit is set, then that number is going to be present in one of the subsets, and if it is not set, it is not going to be present in that subset. So suppose so we know that it's 2 to the power 3, so we can have 8 numbers. So let's take 0 0 0 0 0 1 0 1 0 1 0 0 0 1 1 1 0 1 1 1 0, and then the last one is 1 1 1. Okay, so we have these 8 numbers. Now what we can do is, we know that this number is 0 0 0. Okay, and each of the bit is essentially one element of the array. Suppose we allot this 1, this is 2, this is 3. So for the first number, what we'll do is, we know that none of the bits are present, so none of these 3 elements is going to be present in that subset. Now the second one is 0 0 1. So in this case, we know that this bit is going to be the number which is being represented by this bit is going to be present, and rest of the numbers are not going to be present. So this is 3. Now in this, we are going to have 0 1 0. So this 2 is going to be present in the set. Then this is going to be 1. And similarly, we can have all these where the combination of 2 elements is there in the subset, and the last one is going to be 1 1 1, where all the bits are going to be present and all the elements are going to be present in the subset. All right, so we understood like how are we going to do it, but to understand, to write a program for it, let's see how we are going to do that. Okay, so this will summarize basically all the steps that we did. So first we are going to calculate the length of the array. It's a very basic one. Then we are going to generate all the numbers from 0 till 2 to the power length, that is n, that was 3 in our case, minus 1. Why? Because when we represented the numbers in binary notations, our numbers went from 0 0 0 till 1 1 1, and this is nothing but 7, which is 2 to the power 3 minus 1, 8 minus 1. All right, so we are going to go through all of these numbers, and then what we are going to do is, since we know that each of the bits is going to represent a particular element in that array, we are going to traverse that array and insert it if that particular position is set in the number or not. So let's do a dry run of this. So first number from the first value of I is going to be 0 in this case, because we are starting from 0. And now we are going from 0 to L minus 1, that is we are going to traverse the array. All right, so J is 0 and our array is something like 1, 2 and 3. So we are checking if the jth bit in I is set or not. Okay, so if this bit, basically the first position, is set or not. If this is not set, then we are not going to insert that element in the array, and if it is set, we are going to insert that element. So in this case, we know that the jth bit, that is the 0th bit, was not set. So this was not included in the array. Now, the second one will go and will check if in the original number, the ith position, that jth position, that is the first position, was set or not. So we know that this wasn't set, so even 2 is not going to be included in the array. Then the third one will check, and we know that this is not set, so even j is equal to 2, that is 3, is also not going to be present in the array. So this will give us the empty subset, then empty array, which is one of the subsets of the power set. Now suppose we have the number like 0, 1, 1. So in this case, when we traverse from 0 to L minus 1, that is 2 in our case. So for j is equal to 0, sorry. Yeah, for j is equal to 0, we are, sorry, just a second. Yeah, for j is equal to 0, we are going to check if this position was set in or not in the ith number. And since this was not set, we are not going to include the 0th element. Now we are going to check for the second position, that is j is equal to 1, and we know that it is set. So we are going to include this element in the array. So that is 2. And for same goes for the third one. We are going to check if this position was set, and yes, it was set. So we are going to introduce it, insert it in that array. And this way we are going to achieve all of the subsets of the power set. I hope I didn't confuse you all.
I think if you take I as incremental, right? 0, 0, 0, 0, 1, right? And 0, 1, 0, and then 1, 0, 0. If you take these 4 numbers and then see what gets inserted into A, right? You can easily visualize, right?
Mm-hmm. Yes.
Yeah.
All right. Okay.
Vivek, yes, it's going to be exponential time because we need the power set, right? So the numbers are going to be exponential, right? It would expand out to that level. So the time is going to be exponential because it is superset, right? Yeah.
Okay.
Yeah, just give me 1 minute. I'm not able to erase this. I'll just join back some of this. Yeah, just give me 1 minute. Meanwhile, you guys can ask any questions if you have.
Yeah, so for this same question, right, if you take I equal to 0, 0, 1, right, so you would be inserting actually 3 first. And if you take I equals to 0, 1, 0, you would be inserting 2 into it in the A. And if I equals to 1, 0, 0, you will be inserting 1 in the power set, right? So
Yes.
So if you go to the next part, which is I equals to 0, 1, 1, right? In this case, as Shriya explained, 2, 3 would come. So like that, 1, 3 would come and 1, 2 would come. So that's how the power set is built.
Okay, there seems to be some problem actually. Just give me 1 moment. I'll just share my screen once again. Yeah, all right. So shall we move on to the next one? So this is basically the last question of this session. We need to find the complement of a number. Okay, so if we have been given a number like 101, then the complement of that number is going to be 010. All right, so we know we can use this operator, but we want to do it without using this operator actually. Okay. All right. Yes. So what we are going to do here is we need to find some way of inverting the bits of the original number one by one. Okay, and we know from the previous questions that if you want to invert any bit, we simply try to XOR that number with 1 and the bits is going to be inverted. All right, so this is going to be 1 and this is going to give us 0. So what we need to have is simply we need to have a mask such that all the bits in that number is going to be set, and we simply perform the XOR of these two numbers. So yeah, so this will give us 0 1 0, which is simply the complement of this number. Okay, so now how we are going to achieve this mask where all the bits are going to be set? First of all, we need to know how many bits are present in our number. Okay, so that we can easily calculate by, because we know that any number can be represented in the power of 2. So whenever we try to take the log of that number, it is going to give us the number of digits, and add 1 to it, it is going to give us the number of digits present in that number. Okay, so what we'll do is we first count the bits in that number, that will be given by log 2 base n plus 1, and then we are going to form a number such that all the bits in that number are going to be set. And how we are going to achieve that is basically, suppose we need a number like 111, so that can be achieved using an operation something like, okay, so let's try to have a number x where we try to left shift by the number of bits in that number. Okay, so what will happen, okay, so let's try to have a number 1 and we'll try to left shift by c positions, that is in this case it is going to be 3. So what we'll do is this will add 3 zeros to this number. Okay, but this is not the number that we want to achieve. However, we know one more thing, that if we try to subtract 1, all the bits till the first set bit are going to be inverted. So this will result in 0 1 1 1, and hence we are going to get our number which we need to use as a mask, and then simply we can perform the XOR of this number with the original number to achieve the complement. Okay, so this is basically the steps that we are going to perform in this. First we calculated x, that is the number of bits in that number. Then we tried to form a number m, and to achieve m minus 1, that is achieving a number with all the bits set to 1, we tried to do m minus 1, and then we simply XORed the original number with that mask, and then we get the complement of that number. So any doubts here? All right. So, okay. So this brings us to the end of this session. There are 2 small questions for you to solve. And since we have time, we can do it right now. So this is the first one. So I hope you guys are able to see my screen and solving the question.
One hint is to use XOR operation to get started.
Yeah, okay, Vivek. So by doing A's or B, you're going to get a number where all the bits are going to be set, where A and B are set, and rest of the bits are going to be where A and B are different. Otherwise, it's going to be 0. But how are we going to know if they differ by 1 bit or not? Okay, so let's try to, number should be a power of 2. Yeah, so most of you got it right. So yes, Swapnil, the number should be a power of 2, but that number is going to be A's or B and not the original number. Okay, so yeah, that's the correct answer actually. So what we'll do is, suppose we have a number A like 1010 and B is 1110, and if we try to perform A's or B, then the answer in this case is going to be 0010. And you can see that there is only one bit set, right? Hence, this number is going to be a power of 2. So we can simply apply the algorithm to checking whether a number is a power of 2 or counting the number of bits, that if there are 1 or not. So yeah, this can be done in this way. Now, the second one, we learned how to set a particular bit of a number. Okay. Now, how are we going to set all the bits in a given binary number, within a given range? So, for example, we have been given a binary number 1001, and the range is left is equal to 2 and right is equal to 0. So since this is 0 and this is 2, so what we want is that all these bits are going to be set. So how can we achieve that? Okay, so one hint I can give you here is, like when we wanted to set a particular bit, we wanted that at that position, the value of our mask should be 1. Okay. And we performed an OR operation, because if we try to do OR of any number with 1, it will give us the same number. Oh, sorry, it will always set the bit. Okay. So suppose we want to have L is equal to 2 and R is equal to 0, and all these bits need to be set. We need to have a mask such that if we take a number, then all the bits which we want us to be set should be like this. Okay, so we have one answer by Kiana. Let's try that. So suppose she says that for I in range L to R, so basically we'll try from 0 to 2 and we'll perform AND. Okay, so since our number was 1001 and we try to do, okay, so first we'll do 1001, sorry. We try to do 1001 and we'll do AND with 1 left shift by 0 position. So this will give us, so this is 1, this is going to give us the same number, and then we'll try to do the left shift by 1 position, that is 10. So this is going to give us something like, okay, so this is going to give us something like this, and if we perform it with the original number, then it is going to give us something like this. Yeah, it's going to give us something like this, but we don't want that. We want all these bits to be set. So if we use AND operator, this will never happen, because one bit is always going, if it is 0, then we're not going to get the bit as set. Yeah, okay. And if we try to do OR, so maybe if you try to do OR, then you can get the answer. And we have one more solution from Vivek. Okay, I'll just give you guys one more minute. All right. So, yeah. So actually there can be multiple ways of achieving this mask. I'll just tell you the way which I try most of the time. So what we can do here is we need to have a mask such that all the bits from L to R are going to be set and the rest of the bits can be 0. All right. So we know from the code which we wrote in the complement of finding the complement of a number, we know how can we achieve a particular a number such that all the bits in that number are set. Okay. So if we try to form such kind of number that, okay, so this number can be simply formed, we can simply have this number from what we used in the complement method, like performing the move, so by performing m minus 1, and where m is basically nothing by 1 shifted by the number of the size of the number actually. So in this case, we want that it should be something like r minus l plus 1. Okay, where r is the upper bound, this is the lower bound, and this. So if we wanted in the range 0 to 2, we wanted 3 bits to be set in that case. Okay, so 2 minus 0 plus 1, that is going to be 3. So we want something like this. So if we try to achieve this, so this will give us 1 0 0, and doing minus 1 on it is going to give us 0 1 1 1. But this is not the number which we want to AND with. We want that this number should be lying in that range from L to R. So what we can do is we can simply do a left shift on this. We can keep on shifting this number till we have reached this point. Okay. So from basically from this end. So suppose we want to do a left shift. So because we know that the range is starting from 0. So if we try to shift this number by 0 positions, then we can have this mask. And had the range been something like this, we would have shifted this number by 1 position, that is the lower bound, towards the left side. So we can achieve a number like 1110. All right. So yeah, this was the code for that. So this X, we are counting the number of elements where we want to have the set bits. Then we are simply computing that, and this L represents the lower bound, and we are shifting the original number towards the left by the lower bound and simply performing the OR with the original number. Okay, let me know if you guys have any doubts. So if there are no doubts, we can conclude this session. Thank you all for attending this session, and I hope you were able to learn something today. Yeah. Handing over to you, Hussaina.
Yeah. Yes, it was a good session. Thanks, Shriya. We can continue the discussion on the Slack channel. This is the channel for this session. And we are also concluding this series with this session. I hope you gained or learned something new from these sessions that we had organized. So we would like to hear any feedback, and do let us know what you want to hear in the next sessions. So thanks again, and all the best for your interviews. The recorded sessions will be available on YouTube. I can share the link on the Slack channel, and we will also update it on the meetup page once it is available. It would take a couple of days to upload it. Let's wrap up then. Thank you all for joining. Thanks, Shriya.
Yeah, thank you, Hussaina. Welcome.
Yeah.
Okay, bye-bye.
Thank you.
Bye.